I'm recording.
Jodie recently completed honours with supervision by Dietmar and Rohit. I don't know how many other people.
Oh, I can introduce myself. Yes.
Oh, good.
So my official supervisors were Tristan, who's like the architect of Pi Badlands / Baselands, and Jodie, who's a reef scientist, marine geologist. I just finished my honours project. I haven't gotten my results yet, but I'm going to give you my presentation now. First, I'd like to acknowledge the Gadigal people of the Eora Nation, whose lands we're currently gathering on. This has been a place of learning for thousands and thousands of years, so I pay my respects to elders, past, present, and future, and the current community. And I'll begin my presentation. Great. So my presentation was essentially trying to model the response of different coral communities to environmental change with Bayes Reef, which combines a forward numerical model within a Bayesian framework, Bayesian inference framework, to have a more statistically robust approach to numerical modeling. So first, I'm just going to go through some background to get you familiar with with the geology of reefs, and then go through my methodology and my results. So to give some background from ecological studies, reefs are living organisms, and corals are living organisms, and they're very sensitive to their environmental conditions, which include, among other things, accommodation, which is the amount of vertical space created for a reef to grow, and it's a function of, among other things, the rise in sea level and the reef surface growing up to meet the ocean surface. Also hydrodynamic energy, which is the combination of waves and currents circulating in lagoons. So that's hydrodynamic energy, and also winds, which amplify waves, and also reef-derived sediments. And so that's like carbonate sediments, and because they're very small, they get resuspended by waves and create murky water or turbid conditions. And the other effect they have is sediments on corals can smother them and cause mortality. And so a combination of these effects determine ecological niches within which different corals and coralline algal species coexist. And so that would be called an assemblage of, or a coralgal assemblage, so an assemblage of coral species and coralline algal species. These environmental factors also vary across the reef and with depth, and you can see that with the wedges that I have here. So turbidity is usually greater on the protected margin. Hydrodynamic energy is usually greater on the exposed margin, the margin exposed to waves. And also each assemblage usually has a tolerance threshold, so like a range within which it can exist based on these environmental conditions. The tolerance thresholds as well are not really well constrained in geologic time. They might be constrained ecologically, so like on meters, or like on seconds to days kind of thing. But it's rarely these things can't be measured on anything greater than a 10-year scale. But that's kind of what we're interested in. And so there's an inverse problem where you can't observe how these processes of hydrodynamic energy affect reefs, but we want to be able to infer these because you want to see the long-term response of corals to different environmental conditions. And so under the living veneer of corals, there is you can drill down and see the environmental history of corals, which is what we're trying to examine in the study. And that's called a drill core. So by examining the patterns of assemblage changes that you see in a drill core, you can see how assemblages have changed based on environmental conditions. So this would be called paleoenvironmental analysis. And based on paleoenvironmental analysis of drill cores, so kind of looking at what the most dominant species are in a core, you can come up with some idealized reef sequences like this one by Belinda Dechnik, who was part of the Geocoastal Research Group. And so what you see here is a really classic shallowing up sequence, and this was developed by Belinda in response to changing accommodation space and changing hydrodynamic energy. So what you see at the bottom, at the base of the core, where paleo water depths were great, so between like 20 and 30 meters depth. You see massive turbidity tolerant assemblages. As paleo water depth decreases, then you get these branching assemblages that can withstand greater wave energy. And then in about 6 meters paleo water depth, you get robust branching corals that are very tolerant to waves. The problem with this kind of theoretical diagram, or like this conceptual understanding of reef sequences, is that firstly, it's qualitative rather than quantitative, and so it doesn't say anything about the thresholds of each assemblage to the environmental conditions. That's actually one of the main things that we're looking at in my thesis, because we want to be able to distinguish like the thresholds on longer timescales, but you can't read them from a core. So instead, I used PyReef Core, which is a model that models the processes, the environmental processes of changing hydrodynamic energy conditions, changing sediment input and accommodation space. And then you can observe these processes over time and how they contribute to changing assemblages. And from that, you can see what the exposure thresholds are of each assemblage. The reason why this would be important is because, first of all, in and of itself, it's important to understand how reefs in the past have responded to climate change or environmental change. And also because in the future, or like using this kind of predictive model in the future might show or might help us determine how reefs will respond to catastrophic climate change. So PyReef Core is a forward model, which means it's a deterministic model that simulates the processes of sediment input, hydrodynamic energy, and changing accommodation, and models its effect on ecological dynamics, which is the kind of interactions between different assemblages. And we model that using a predator-prey model. It's also called a Lotka-Volterra model, if you're familiar. It's basically encapsulated in this algorithm where X is the population of a specific assemblage, and so the population is determined by a Malthusian parameter, which is the rate of growth or decrease, and also an interaction matrix coefficient. And so this is the interaction matrix here. And it basically says that for every pairwise interaction between two different assemblages, you either have competitive interactions or neutral interactions, which means they don't have an effect on each other, like two populations can coexist. And so if there's competitive interactions, then this value would be a negative, and if there are neutral interactions between assemblage I and assemblage J, then this value would be positive. So these things determine the ecological dynamics. The other thing that is part of the PyReef model is these environmental thresholds, which show that it basically shows the range of conditions for water depth, sediment input, and flow velocity upon which an assemblage will grow at 100% of its maximum growth rate. And elsewhere, it will grow at a decreased rate, or it won't grow at all. So this reflects the fact that, corals are very sensitive to their conditions, won't grow or won't thrive in conditions outside of a very narrow window. One of the features of this kind of stratigraphic forward model that produces a core like this is that it has non-unique solutions. So there might be many combinations of environmental factors that create the same kind of observed core. This is something we know intuitively from geology in a number of geological problems. The other thing is using a stratigraphic forward model on itself does not quantify any kind of uncertainty, and there is uncertainty inherently in the assumptions that propagate through the parameters to produce uncertain results. An example of that is that we don't actually know at what depth you get these transitions between different kinds of assemblages, and theoretically you could create some kind of distribution of where these occur, but the problem is we don't really have enough data for that. We don't have enough cores drilled logistically to create a probabilistic model of where these transitions occur. So we don't actually know what that would look like. And so that's why we're using Markov chain Monte Carlo approach to accommodate the missing data problem, because we don't actually know enough about some of the parameters that we're using as inputs for the model. And also the inverse problem, which is that you can't observe some of the things we want to measure using a classical paleo environmental analysis approach. That's why we're using a model. And so I used Bay Reef in my thesis to be able to calibrate models to data, also to quantify uncertainty in the models, and to estimate the model parameters. So the kinds of things that we can't see in the fossil record, but we still need to know.
Could you talk a bit more about what data is missing?
Yeah, okay. The kind of data that's missing is like when you have a reef, there are only logistically some parts of the reef that you can drill, like the windward front or like the hard margins. It's really hard to drill in a lagoon, mainly because the core that you would get would be filled with sediment, and so your recovery of the core would be very low because all the sediment gets washed out. And so there's a bias towards the kinds of data that you have when you're drilling through a reef, which is it's biased towards the margins. And it's not representative of the structure of a reef all the way through. So yeah, that's like one example of it.
Missing, not at random.
Yeah. Also, we don't have data on every single reef kind of thing, only on some that are really accessible to people. So we used pseudo likelihoods because there was because obviously you can't analyze the probability of obtaining different kinds of cores. So we used pseudo likelihoods rather than a typical likelihood function. So in this case, we replaced maximum likelihood estimation with a mean squared error minimization calculation to approximate the posterior probability rather than probabilistically finding the true underlying distribution. So it looks something like this, where theta is the vector of parameters. And so in our case, we're looking at between 15 and 50 different parameters. DSIM is the simulated data, which is deterministically found from the parameters. And DOBS is the observed data core that we're trying to compare with. At the time of writing my thesis, the theoretical properties of this algorithm hadn't been investigated. And it's kind of based on the assumption that the models are normally distributed, which we're going to interrogate further and see if that actually holds.
Okay, so what she does is you draw theta from some distribution and that's part of the MCE scheme. Then you use a forward model to go from theta to the DSIM, and then she says that that's the mean of the likelihood function for the observed data. So basically, theta goes to simulated values. The forward model gives a mean function, is the mean value of the actual observed data, and it's disturbed. But the data is discrete; it's not continuous. So, but we're just working on figuring out different likelihoods, essentially, rather than that implicit Gaussian one.
Thanks, Ali. Yep. So the parameters that include the Malthusian parameter, which I mentioned earlier, we had only two assemblage matrix values for simplification, and then 4 values each that defined the exposure thresholds to sediment input, to flow velocity, and we had to compute those for each assemblage. So this represented like a lot of where the parameters, so we had like between 15 and 50 parameters, and the bulk of that is in like trying to figure out what the exposure thresholds look like for each assemblage. We use uniform priors for each parameter that's used within a range that was defined based on literature studies, like based on what you would find in the literature, right? Does that make sense? Sure. The proposal jump width was defined for each parameter because they were orders of magnitude different. And we used the Metropolis Hastings acceptance decision as well. Used a burn-in of 5 to 10%, and then a convergence statistic to measure how well it converged to the data, which is a combination of the root mean squared error and also the proportion of sediment in the core. And that's because we're trying to minimize the proportion of sediment in the core so that it is mostly corallable growth rather than just filled with sediment. So my objectives were to prove that Bayes Reef could work efficiently, accurately, and robustly, and also to show that it's a useful tool. Because of the non-unique problem, I can't say that it worked with accuracy, but it did work efficiently and robustly in the simple case, which I'm going to demonstrate now. So first I needed to prove that this algorithm could work. So I had a proof of concept experiment where I used a simple shallowing up sequence as synthetic data and tested for the ability of the algorithm to take a random set of parameters and eventually converge on this synthetic core. So the chains were run, the MCMC chains were run for 50,000 samples. So that took about 5 days per chain. I controlled for the dimensionality of the experiment, so 15 versus 27 free parameters. And then I assessed it for accuracy, robustness, and efficiency. In terms of accuracy, you can see that, both the cores do fit synthetic data well. This is the synthetic data, and these were the best, or like the mean estimate models. And this is just a summary of like what the area is down the core, and also, to quantify that, the root mean squared error was slightly lower for the constrained experiment at 0.066, and it wasn't so different from the unconstrained experiment. They were both quite good fits with data. Regarding uncertainty, you can see that the bulk of uncertainty is focused at assemblage transitions. So what you're looking at here is like, this is the core with depth. So this is the top of the core and the bottom of the core. And here are the categories of the different assemblages here, and where there was no assemblage growth, there was the sediment. And the black line shows the transition between the different categories, and the dotted lines show the 90th or like 90% confidence, credible interval, and then the mean is shown by the green line. So you can see that they have comparable levels of uncertainty. However, the unconstrained experiment was slightly better at predicting at approximating the data in the lower part of the core. Regarding parameter estimation, the observed parameters were not actually within the credible interval of the point estimates. So the observed values, or the values that we used to create the synthetic experiment, were like 2 to 3 orders of magnitude lower than what the posterior distribution, or like the point mean of the posterior distribution gave us. So in both cases they were essentially inaccurate, which poses an interesting conundrum, because the models were really good. Like the model estimate after running the MCMC was really good, but the parameter estimations were really off. And one way to explain this another thing is that both the parameters and the model solution space is multimodal, which does provide a solution for why this is occurring. So like I mentioned previously, the stratigraphic forward models are non-unique, so different combinations of parameters can produce the same solution, which means that the MCMC approach was able to find like one good solution, maybe like a local optima, but not the global optima. And that
may be multiple global.
That could be the case as well. And then even with added dimensionality, there was like, for the simple case, both experiments could produce similarly accurate results, which showed that like dimensionality wasn't actually a problem for the MCMC algorithm. In the end, the proof of concept experiment shows that our algorithm worked for the simple case. So following on from that, I tried to do an application to something a bit more complicated, because not all reefs are like this. Sequence doesn't represent all reefs. In fact, they're far more complicated than that. You get a lot more transitions between assemblages, and they don't always follow like what you think you would see. What I wanted to do was try and test phase reef on noisy data. So essentially things that are like a bit more realistic but complicated, and then use that to predict the exposure thresholds of assemblages to hydrodynamic energy and sediment input. And of course, this is a thing that is useful to anybody studying reefs. It's like understanding the long-term response of corals to changing environmental conditions. So I picked 3 different cores to compare it to, and I picked them based on the fact that Heron Island, which is the one up here, and One Tree Reef both have very, very similar assemblages. And they like 2 of the cores were on protected margins and 1 of them was on an exposed margin. And so the idea was, because they exhibit similar coral assemblages but are in different environments, hopefully they can come up with the same exposure thresholds, because, or at least for the 2 protected ones on the 2 protected margins, hopefully they'd have a similar response to environmental conditions if they occurred in roughly similar conditions to begin with. And so I ran the MCMC chains again for 50,000 samples to try and calibrate the model to the models to the core data. And what we found was that the chains didn't actually converge on the optimal solution, or that there was a lot of uncertainty around the optimal solution, and the most optimal models were like only visited infrequently. And because of that, and you can see, because the mean convergence statistic was very different to the optimal convergence statistic. So this meant that like the posterior distributions wouldn't be representative of the optimal data. So I couldn't really use like a Bayesian inference approach here. So instead I used a classical optimization technique. Like I picked the best model that was taken, or the best model that was predicted by each chain, and then analyzed that.
What is convergence statistic?
The convergence statistic is kind of like the RMSE combined with like the proportion of sediment. So it's just basically a measure of how well the data fits with the model.
It's not about how well the chains do.
Yeah, no, it's not. So maybe that should be changed to some other name, like fit statistic or something.
Which audience you're giving it to, I suppose.
True. For brevity, I'm only going to look at one of the experiments that I ran, because not much time, and this one actually produced the best, one of the best results. So this is the Heron Island core. This is actually what the data is, and this is what the model predicted, and this is what the data looks like, and this is a summary of error. So you can see that there's like 2 main intervals where there was error between the model and the Heron Island core. To be clear, the model was like based on the MCMC chain. It was like the best predicted set of parameters, like the set of parameters that produced the best predicted model in classical, because I used a classical optimization approach. The RMSE was less than 0.1, so it was quite a good fit. However, it reached, so here we're comparing on the basis of the depth structure of the cores, but if you actually looked at the time structure, you would see that this is a representation of it, the core actually reached sea level about 4,000 years before the actual core was observed to reach sea level. So it basically grew the core really, really fast. So coral was growing at a rate that was far higher than what we observe in real life. And that's partly because we just weren't we weren't comparing data with the model on the basis of the time structure. This is something that we're going to look into in the future, because time structure is almost more important than depth structure in this scenario, because essentially it's like useless if you can't match the timings. So to demonstrate how it can be used in paleoenvironmental analysis, this graph here demonstrates the kind of like environmental conditions for each assemblage. So you can see that like the shallow exposed assemblages, which are these 2 purple circles, are very wide, they're very broad. These assemblages can exist in a variety of hydrodynamic and sediment input conditions, whereas the deeper assemblages can only exist in a very small window with only a small amount of sediment input and a very small flow velocity. So if you were to use this as a tool that can guide further inquiry, then you might want to test whether this actually holds in real life. So you might want to use this as a hypothesis and then test on these kind of assemblages, because they exist now, whether this hypothesis holds. So to conclude, I think this person called George Box, who was writing about stratigraphic forward models, said it really well. He said, all models are wrong, but some are useful. In this case, I think that the significance of these results for paleoenvironmental analysis doesn't really rely on how accurate the results are. but more the greater purpose is is heuristics. So being able to diagnose MCMC problems, figure out what assumptions are erroneous in the stratigraphic forward model, and also generate kind of hypotheses that can be tested, in the ecological domain, or like tested to see if this holds for other reefs elsewhere. The results are also insightful regarding improvements to Bayes Reef. So at the moment, we're trying to see if we're trying to change the likelihood evaluation function to see if we can come up with something else that doesn't suppose that models are distributed in a Gaussian way. Also, Bayes Reef was able to find optimal solutions, but with uncertainty. So the Bayesian inference approach isn't working all that well for complicated or noisy data. So that's something that we need to obviously look into. So that might be a refinement of the data, or again, something to do with the model, I would say. And finally, because the posterior distribution didn't represent underlying data, we couldn't use Bayesian inference, but if we could, then you'll be able to quantify uncertainty. So it is still a really useful method. It just needs to be worked on a little bit. So finally, my final conclusions are that the sampler did work robustly and efficiently for the simple case, and with fewer free parameters, but wasn't so efficient when calibrating to noisy data. We're working on modifications to the algorithm. And finally, it's a really useful tool for quantifying uncertainty in models, which was previously really tedious if you're just using a stratigraphic forward model and you're just manually changing parameters. So this is useful in that the sampling algorithm increases the efficiency of being able to apply these models. For observing unobservables, so for being able to measure things that you can't see in the geological record. For efficient model selection, which, as I was saying, it's really tedious if you're just using a stratigraphic forward modeling approach to pick which model suited best. And also it can be used for obtaining a 3D picture of reef system evolution. So like I mentioned before, it's really difficult logistically to get drill cores on different parts of the reef. I'm sure you can imagine that, you have to set up a really large structure on a reef. It's very expensive. So being able to model parts of the reef that you can't access is very valuable. And so, you would be able to use this tool to constrain some factors by looking at data and then trying to extrapolate that to other areas of the reef. And so that's the main benefit to anybody studying reefs. And that's my...
Can you ever...
Yeah.
So would it be of use to be able to say, if you had one drill that you could take, where should you put it? Is that sort of information useful? Or you just simply can't drill?
No, that would be useful.
Yeah,
but the part of this I think is so exciting, is you're never going to have enough drill cores. That's just you can start off with that sort of
It's
assumption.
the small data problem.
Yeah, and understanding, or at least having a better understanding of how these systems vary spatially and temporally.
Yeah.
I just think modelling is the only way, and being able to quantify the uncertainties.
So then, as Sally was saying, you could sort of try to find the locations where you make the holes to be able to maximize the information gain.
To reduce your uncertainty. So if you want to think about it as, I want to reduce my uncertainty most, and I've got a certain budget for getting a hole. Where do I take that hole? That will increase my information gain. Also, the other thing is that the reason what's really will, I think, make the models a lot, they'll be able to find posterior modes, is actually we just need to work on the priors. So an inversion problem is one when there are multiple solutions, and the way that we get around that in Bayesian statistics is by regularizing it with a prior. So if you force the priors, because they were quite wide priors, remember?
Yes, they were quite wide.
So we need to bring more of your knowledge into the construction of priors, and then we'll get better posterior estimates.
That's true. In regards to using this as a tool to identify where to drill, I feel like intuition kind of guides that. So the fact that people do try and drill in the lagoon and find that those have the lowest core recovery is what determines where you drill. Just knowledge in the past about where you would get good recovery and where you wouldn't.
It'd be nice to quantify how much you're going to reduce your uncertainty by if you drill here, point A versus point B.
Yeah, and I guess what I would say is that the underlying motivation for all of this is to, at least for me, is to understand. The reason we dig holes in the ground is to understand how the past reef has evolved in response to environmental changes, but it is really all about trying to better predict. Right, like Jody showed it, the little cores going into the future, right? And so that's really the underlying motivation. Now, can we get a better crystal ball? Right? Can we make better, more informed predictions on how this reef will respond if we have, for example, rising sea level
seas
of a certain rate, or sediment flux of a certain rate?
So in that sense,
More
it would be
intense
useful
storms.
not just to reduce your uncertainty across the overall space, but try to find the locations that you think mimic what could happen in the future.
Yes. Yeah, and hopefully allowing us to understand why in one place the communities, we have these sorts of communities there, in another place we have a different set of communities.
So it's also more than just prediction. You want to understand, you want to infer something. about the
Yeah,
process by which you're
exactly.
operating.
Exactly, yeah.
Exactly.
Oh, it's very interesting. Because I like the name Bayes Reef. It reflects what we do.
So as you said, like with models are never perfect, but you can use them to learn something about what drives the evolution.
Yes.
Do you think that what you've seen so far, even though the MCMC converged on the solutions, do you feel like you can learn something? I've learned something about specific parameters within that one. What it's more sensitive to.
Yeah, well, I thought that this phase diagram might elicit something like that. Basically what this shows is that the shallow assemblages, so things that grow in less than 6 meters water depth, from this you can see that they're not really sensitive to flow velocity or sediment input, which is interesting because that might pose the question why don't they occur everywhere? But I guess that's kind of explained by the fact that anything that occurs deeper is actually really, really sensitive to sediment inputs. I don't know if this has been, I'll have to find out. I don't know if this has kind of been inferred before, but I think it is something that can be tested, whether shallow assemblages are really robust to environmental changes, because then that might say something about how likely they're going to survive into the future when seas are rougher because of more intense storms, etc.
Yeah, and it's important to note that Jody's sort of playing with essentially 3 environmental parameters, and so we actually know there are many more environmental parameters that aren't at this stage being considered in the model.
Yeah.
But this is really, really powerful because at least in this context, it's allowing us to say that, okay, these parameters are less important than others, even if it appears to be, even if it's telling us it's insensitive to those other ones.
Yeah.
Again, it allows us to then think about, okay, what environmental parameters are driving those things to be where they are.
Yeah. And one of the prevailing models about, reefs, the changing of reefs vertically, of different assemblages vertically, is that accommodation space is the main control on that, which is just essentially sea level rise. But we know it's more complicated than that, but so far there aren't that many theories that relate how sediment input affects, the vertical growth of corals on long time scales. And so even though it's just, this model is only looking at 3 environmental parameters, that's still challenging the paradigm that only, depth is that only depth really influences what goes where. Yep, any other questions? Great. Thanks for coming, everybody. Yep, excellent. Do you want me to stop this, Ricky?
Yes, end